Hello everyone, my name is Mahbod from Concordia University, Montreal, Quebec, and today I'm presenting our work, which is a collaboration with my co-authors from Concordia University, École de technologie supérieure, and National Research Council of Canada. So in this work, we have worked on a case study on IFC validation and information requirement, and the question that we are trying to answer today is is our building data actually ready to be used? So let me start with some context here. So we all know that buildings use a huge part of the world's energy, and that in return, they produce a large part of CO2 emission. And this is mostly coming from the existing buildings. So retrofitting these buildings is one of the best ways to actually reduce the energy use. However, traditional retrofit planning uses static data like all-weather records and like fixed numbers, and this often doesn't match with how building really behaves. And this is called energy performance gap. Digital twin, however, offer a better way, and a DT is a live digital copy of a building. It uses real sensor data, and the data is updated constantly, and it can support better retrofit decisions. But a DT can work properly only if the data behind it is good enough. And this data mostly come from BIM converted into IFC format. So here is the problem. When a BIM model is exported to IFC, sometimes most important information is missing, or they are not included in the model from the very start. And three things that can go missing most often are thermal properties, material definition, and equipment specifications. And this is a serious issue because without this information, we cannot link the model to actual building systems like energy management systems or IoT sensors. And the result could be longer project time, and also the result that we cannot fully trust. So now the problem is known, but a few studies actually define the requirements needed for this kind of project and actually check for them automatically before a DT is built. And this is the gap that we are trying to address here. Here is our research question: how we can clearly define the minimum set of requirements for retrofit projects, envelope retrofit to be exact, and automatically check if the IFC model has this information to support DT use. And this paper tries to make three contributions. First is defining a minimum set of requirements for envelope retrofit. Second is turning these requirements into a machine-readable format called IDS, which is Information Delivery Specification offered by Building Smart. And third is demonstration of a working automated process that checks a real IFC model against these requirements. Here is how we did this work in 5 steps. The first step, we identified the information needed for envelope retrofit based on literature and common practices. Then we turned these requirements into IDS. The building model was created and exported to IFC format. Next is validation of the IFC model against the IDS rules, and then we analyzed the results to find a pattern in the data gap. And one important point here to mention is that our results check whether information is already included in the model, and they do not force any specific modeling method or a specific data value. Let's take a look at our case study. This is Future Building Laboratory, or FBL, located in one of Concordia University's campus in Montreal, Quebec. This is a single-story research building. On the right, you can see the actual 3D model of the building as it appears inside the validation tool. And we chose this building because it's a realistic, small-scale example. And the B model, most importantly, was exported to IFC4 without any manual correction in advance. And this helps us to have the raw export and the report actually after the result, not a cleaned up best version. Now, what exactly did we check? We focused on 5 building elements that are central to retrofit because these elements control how the heat goes in and outside the building. And these are walls, roofs, slabs, windows, and doors. For each of these elements, we check for 3 things: correct identification, material assignment, and thermal performance data. And we deliberately left out some information, for example, sensor data or performance target, because this kind of information either is not included or live in the IFC, or they are hard to track among different tools. And keeping the scope focus made the validation practical and repeatable. So this table summarizes what we required for each element. For example, for external walls, we required most properties. And actually, the reason is that walls play the biggest role in the heat loss, so we treated them as the highest priority. And you can see the rest of requirements for the rest of elements as well. And in general, for the solid elements, we asked for identity, material, and thermal data. And for openings, thermal performance was the priority. So let me quickly explain the tools that we use. We build our rules in OSBIM. This is a tool specifically for writing the IDS tools without any codes required. We built a model, 3D model in Autodesk Revit and exported that to IFC4. And then we validated the model against the rules by using BIM Collab Zoom. And these tools check every applicable element against the rules and produce the results as pass or fail. And most importantly, we have the reason as to why the fail happens and which property is missing. And this is something that helps us divide the geometry data from semantic data. Now the results. A large number of elements failed at least one check, but the pattern was very clear. The geometry was almost fine and correct, but the missing data was semantic, material, and thermal information for the elements. So for example, for the walls, the material was often not assigned, or thermal properties was missing, and even some internal walls were flagged as external. Also, this is the story same for the rest of the elements. Geometry, yes. Thermal and material data, no. And let me show you what this actually looks like directly from the validation tool. On the left, you can see the screenshot from BIM Collab Zoom checking the doors. It shows that 10 doors fail the checking. And when you take a closer look at the property, you can see that some information, for example, even fire rating or is external flag are there, and they are included. It looks complete, but thermal transmittance is still blank. And that's one property missing is enough to fail the check. And the exact same pattern repeated for the rest of elements as well. And this brings us to our main message. A model can look complete, but still not be usable. If you open this IFC file and look at the 3D, it appears as complete. Everything is there, but there's some data behind it is missing. And so this is not usable for data DT integration or like any assessment for the retrofit. 3 takeaways here. First, this is not only the technical problem, but rather it's the process problem. It comes from not defining the requirements clearly enough before modeling starts. And the second, IDS validation is just an early checkpoint. It's meant to catch the basic gaps early before they become expensive or hard to fix. And third, IDS has its own limitation. It checks whether information exists and is assigned correctly. It doesn't check if the values are realistic or physically correct, and it only looks at the static data, not live data from the sensors. And like any other studies, our paper has its own limitation. The set of requirements that we define is only the core subset. We only test this for one building, and also the reputation for the validation was outside the scope of this study. And to conclude, it was realized that the biggest barrier to good retrofit data is not the IFC file format itself, but rather it's undefined requirements, not knowing clearly enough what exactly we need. And when we define the requirements before in advance and automatically check for them, we have the reliable data for decision making. Thank you all very much for your attention.